Okay, so hello. I'm Pete, and I work with Aleph Zero, and I'd love to tell you about smart contracts in Ink specifically, but I guess the first part of the talk will be more generally applicable to, well, other smart contract languages and platforms. So yeah, I felt compelled to include a definition of the smart contract, but well, like a slight remark is that basically the word contract may be misleading to some, as well. Of course, you can think of it as like an actual contract that you enter between the yourself and the code, or your own program and the code. But to be honest, this intuition is maybe not the best. I like to think of smart contracts as basically programs that execute on the blockchain, like treating the blockchain as a computer of sorts. Because, well, the blockchain essentially has like the processing unit, which would be the runtime, and the storage, which would be just the blockchain storage. So it kind of tracks in the whole like computation model. And yeah, that's I think the best way to think about them, like programs that execute on the blockchain. So once we have that, we can build out a lot of interesting use cases, starting, of course, with DeFi, decentralized finance, but then there's some very interesting developments in the digital identity space with all the KYC and KYB solutions, perhaps with privacy included. It's really good space. Supply chain provenance tracking, especially for like bigger enterprises. Quite a hot topic is the certificates of ownership. Of course, NFTs, right? With art, real estate, and you can use the NFTs as a form of like software licensing, or or tickets to events and whatnot. And of course, you can come up with as many use cases as you want. Maybe some GameFi or something even entirely different. So yeah, I think an especially important area is the decentralized finance, right? So basically, think what you know and love from traditional finance, but all put in a very decentralized and permissionless setting. So there's like no trusted intermediary, no bank. It's all just pieces of code running on smart contracts. So in that way, it's very transparent, and you can actually verify what's going on, provided you have some small amount of like code literacy. And examples of DeFi include decentralized exchanges, of course. By the way, you of course know Uniswap. If you don't know Common, this is something that's being built on Aleph Zero. Lending protocols, trading, crowdfunding, payments, whole variety. Basically, actually, you can think of like the whole traditional finance world replicated on the blockchains and using smart contracts. So now, what I kind of wanted to focus on during this talk is like writing the smart contracts and building all this out in a way that's robust, that avoids some common problems, right? So I, kind of jokingly, but not really, formulated this grand theory of hacks, saying that basically an exploit can happen, or probably will happen, in the places in the code where you're not 100% sure what actually happens, right? Maybe you're losing track of some state updates, maybe something happens implicitly, maybe the data is not exactly in the format you would expect it to be, right? So as kind of general advice, this is applicable not only to Ink smart contracts, but I guess even into programming in general, and especially other smart contracts. Like, to avoid that, I would say input validation is extremely important, and in general, like typing your code in the right way, meaning that things should have, like clearly defined types, right? That in general helps you avoid the most common problems. Then mutating the state So like, you know, going to the smart contract storage and actually changing something, that's a risky operation actually, right? It's also inevitable in a sense that, well, your contract needs to update its state in order to function, but I would suggest treating the state updates as kind of like a special operation that you need to do extra carefully, right? And later we're gonna see how Ink actually helps you kind of track these state updates, track in a way that they like really starts to stand out in code, and you know, it's way harder to like mutate the state without even knowing it, right? Actually, and this may sound trivial, but all of the places where the code repeats are quite risky sometimes. So loops, obviously, but especially like recursive code. So functions calling other functions, and especially contracts calling other contracts. This is like a huge, well, I would say, vector for things going wrong, okay? And as we're gonna see in a minute, on like a, well, actually a real world example, the catch-all statements that, you know, whenever you don't know what to do, you call this certain function. This is risky, okay? So just to illustrate, and this is not you know, maybe not very accurate, but just a bird's eye view and a general idea of how the DAO hack happened a few years back. Of course, the issues have been fixed since, but I think this illustrates a really important concept in the whole of smart contract development. So imagine we have the DAO contract, obviously, and we have some actor, malicious actor. So I decided to call the actor Malice, just like the traditional, you know, Alice and Bob. Here it's Malice. I thought it was funny. Yeah, maybe not so much. I don't know. But the DAO contract essentially, well, at least for the purpose of this example, has two functions. You can deposit some ETH, and you can withdraw some ETH, okay? So the attacker first deposits, let's say 100 ETH. It can be actually any number. Now, and then actually immediately the bad actor, the malicious actor, wants to withdraw the deposited amount, right? So what happens is the DAO contract basically checks if the attacker has enough balance. Yes, of course, because yeah, that tracks. This is actually a completely legit operation. So what then happens is that the DAO contract basically sends a transfer of 100 ETH back to Malice. But the way this happens in Solidity is that whenever you're sending money to a smart contract, this smart contract, to like handle this transfer, will call the receive function, right? And if the contract does not have a receive function, it will call the fallback function. And this is what happened in this example. But the way the fallback function was written, it actually contained another withdraw, okay? So yeah, this withdraw call happened again, and you will notice that the DAO contract was actually sending the ETH before updating the balance, okay? And so what happened here is it still happens in context of like one execution step, that the contract does the transfer again to Malice, which again calls the fallback function, which again calls the withdraw function. So basically the loop repeats until the DAO contract is out of funds. And actually an important step in the attack was that the attacker contract was checking whether the DAO contract still has enough funds, because it needed to stop the recursive loop at some point, not to revert the whole transaction because of failure of the last transfer. But yeah, this is basically how they drained the contract of all of the funds. And well, you will notice that it's actually super simple to prevent. You just first update the balance of the attacker's account, and only then you do the transfer. If you flip the order of these instructions, the attack basically doesn't happen. But I think it goes to show that, you know, it's obviously a very basic like reentrancy example, but it goes to show that while smart contracts may look very simple, and you know, like to any seasoned programmer, the code looks like almost like a toy example, the stakes are quite high, right? Because there's users' funds involved, and and sometimes the interactions can get like non-trivial. So yeah, you need to really, you know, write the code in a really safe way and really focus on, well, correctness and safety, right? Yeah. So, well, moving on, we are going to discuss the ink development in context of the Aleph Zero blockchain. Well, if you are not familiar with Aleph Zero, it's a layer 1 proof-of-stake blockchain with some nice privacy features that we are building out. You can read about the liminal framework. We actually have like a developer preview, let's call it. It's called the Shielder. You can check it out all in our documentation. I will actually link to that later. Yeah, the blockchain, well, because basically it's a substrate-based blockchain, but we have created our own consensus, which, well, results in the, you know, both block times and times to finality being sub-second. So yeah, it's really fast, basically. And the transaction costs are really low, which actually is quite important when, you know, thinking about smart contract development, because it kind of can influence the way you write the smart contracts, right? You won't probably have to, like, you know, dive into the bytecode and do some crazy optimizations because it's just cheap. If you're conservative enough with how you allocate storage, so like, you know, if you want to store videos on the blockchain, it's probably gonna get expensive. But if you're like reasonably conservative with your storage, you'll be fine. And a few months ago, we've launched, you know, smart contracts in Ink on the mainnet. So there's use cases building out. We have an ecosystem funding program in place. So we've got a lot of exciting stuff going on. I think it's worth, you know, taking a look at Ink. So if you want to check it out, the QR code, I think, points to our main website, but you can get to all of the other places in like 1 or 2 hops through the links. I would pay special attention to the, oh, let me get the mouse pointer, to the developer portal. It contains some nice, you know, guides and articles that go beyond what I'm going to show here, because, well, my goal today is basically to get you excited about Ink development and not necessarily, you know, walk you through all of the aspects of Ink development. I try to be fairly comprehensive, but this is mostly like, you know, a tour rather than a very detailed tutorial, right? So yeah, what is Ink, basically? Ink is an EDSL for Rust. If you're not familiar with the EDSL concept, it's an embedded domain-specific language. But, well, I think it's best to think about Ink as basically a subset of Rust. So what I'm hearing quite often is, oh, but Rust has such a steep learning curve and it's hard. Well, be that as it may, Ink is not the whole of Rust. And actually, Ink, I think, focuses on just the very basic features of Rust. So everything that is actually hard about Rust development, you won't find in Ink. So, well, OK, the syntax is perhaps new to you, and you will need to, you know, learn like a few types. But for all intents and purposes, Ink is an easy language to learn. I'm not one of those geniuses who just learn everything in 30 seconds, so you can believe me. So yeah, but being a subset of Rust, it inherits some of Rust's benefits. Oh, actually, most of them. But first of all, it's a modern language. So if you look at like the history of programming language research over the last, I don't know, 20 years, like Rust really, and Ink by extension, Rust really like makes use of the like best discoveries. It's type safe. It's like as type safe as a language can be, while still being usable, right? Because you can do some crazy stuff like dependent types and really prove stuff about your code, but then it gets really tedious to write, and you need a PhD. And here, I think it strikes the right balance. Then it's memory safe, and we're gonna talk like very shortly about the memory management in Ink. But I'm seeing that my time is actually running way faster than I thought. OK, yeah. Sorry, I'll need to talk incredibly fast. I'm not on anything. I'm pressed for time. The tooling is actually very nice in Ink. Well, in the context of smart contracts, it's maybe not as mature of an ecosystem as for example, ETHDam. But I think it's, in terms of like, the support for developers, it's there, and it's getting there. So yeah, there's that. And Rust actually is like winning, and has been winning for the past few years, the like Stack Overflow surveys for the most liked language. So I think that's, that says something. I don't know about like last year's, but definitely it's always there at the top. And the next, important feature, or actually a benefit, is that it compiles to WASM, so WebAssembly, which has a proven set of benefits, like ubiquitous, fast, and secure. Obviously, basically runs everywhere, and it's efficient and runs in like a sandbox environment. So yeah, we can say it's secure. Of course, not to say that if you write bad code, it will automatically become good. No, but it helps. It helps. Now, this table, I know it's quite intimidating when you see it on the slide like this, but it really just, I don't want you to really memorize it or anything, but I think it goes to show that, even though Ing is like, it's a new language for many of us, but when you look at like the level of the, like high-level concepts, it's really, compared to Solidity, it should be familiar. Like all of the concepts should feel familiar, right? The exact implementation may be different, and like for example, the storage entries are always 256 bits on ETHDam. They are variable size in Ink, which is actually great for performance because you rarely actually need 256 bits for your like numbers. But in general, if you're a smart contract developer on ETHDam, you should be able to switch to WASM-based contracts and to Ink specifically quite fast and without, like any significant conceptual shifts. This is something that I probably should skip, but I like it. This is just, a fun fact for you. So WASM is basically, you can think of it as like binary format, kind of like regular assembly. But when you actually take the binary blob and decompile it into like textual representation, you see this? You see this familiar little fellow. And if you're like a programming language nerd like me, you instantly recognize it. This is Lisp, right? We all know Lisp. Okay, probably not all, but this is Lisp. This is like a language that's been there for like 80 years. So yeah, but with like a cool modern twist, and executing in the browsers and everywhere. So I like the beauty of simplicity here, right? Because when you look at the code, you notice that there's actually a stack machine. So basically, the whole execution of your program goes like this. And notice how simple it is. If you have an expression like, say, 5 plus 7, you parse it so that you start putting stuff on the stack, right? And you first put the operands, so 5 and 7, and then the operator, the plus. And the whole execution of your program is basically that simple. You pop something from the stack. If it's a function, you see how many arguments it's got. Well, it's got 2 in our case. OK, so we know we need to pop 2 more elements from the stack. If they are not functions themselves, then we are good to go. We can execute. So we just perform the actual function and pop the value back onto the stack. And in this simple case, it's easy, right? We just end up with 12 on the stack. And once we pop it, we know that, OK, the stack is empty. We have 1 result. Well, we've executed the program. But it actually extends very well to even like very complex programs. JVM, I don't know if it still is, but it certainly used to be a stack machine. So like half of the world's software was running on a stack machine. I just thought this is an interesting concept. But yeah, moving on to like a more practical part of the presentation. Again, this is something that may be quite intimidating, but it's just meant to give you like a bird's eye view of what is it like to develop a smart contract in Ink, right? From like the very typey perspective, like what I need to do on my computer to get up and running and actually deploy a smart contract. Okay, so first thing is, as always, installing some prerequisites, some dependencies, some libraries. You just copy and paste a few lines. There you go. Then a concept familiar from every like web framework and that you might have used. You basically, using the cargo contract tool that you've installed in step 0, you basically bootstrap the new contract. It gives you like the whole scaffolding, like a minimal scaffolding basic contract as a starting point. And then you just write your code. OK, then you use the like built-in test suite to run your tests, which are in code. And then you can compile it and upload it to your chain. And there's a joke here that, again, that's maybe not as funny as it was in my head when I was writing this, but you get, well, I'm going to read the slide. You get two artifacts when you build the code, right? The contract's binary code, the WASM blob, the contract's metadata, the JSON, and the like contract bundle, so the two above bundled together. And this goes to show that you need to watch out for off-by-one errors, right? Yeah, this is a good time to laugh, but yeah, don't worry, I can take it. OK, so we are gonna also look at the actual, deploying the contract to the chain, but later, OK? If we get to it, even. So my whole like demo example is the bread and butter of DeFi and smart contracts. So an ERC20 or PSP22 token. PSP22 is basically ERC20, but in the substrate ecosystem talk. I'm calling it Pete coin because I'm Pete and it's a coin, so it kind of made sense. Yeah, when you look at what the ERC20 actually is, it's just a standard and basically a set of questions that your contract needs to respond to. So it needs to know its total supply, a balance of a specific address. Well, we are going to skip allowance and the whole approve and transfer from thing. We are just going to focus on transfers to keep it short, because as far as I know, I have 10 minutes left. Yeah, then it needs to emit some events, but this just goes to say that the standard is just, it's very basic. It just, your contract needs to be able to do a few things, and there you have it. You have an ERC20 token, right? So yeah, well, let's now look at how this actually looks in code, okay? And don't worry, most of the time you won't need to remember how to write all of these macros and everything, because you almost always start with like a bootstrapped contract. So you just need to modify the logic and not really, remember the exact syntax of the macros. I mean, you will just learn it after, the second contract you write, but it's actually not that essential to start out. But yeah, I think an important information is that the lines starting with the hash sign are macros, not comments. So yeah, they basically well predefine some stuff for you, do some imports, enforce certain invariants, especially the inc contract macro. We're gonna see that in a second. So basically, the smart contract is a module. It's a Rust module. And the module is, well, a set of things, of language constructs bundled together. Now, use that we see here, well, it's kind of like importing something, but it's mostly just putting it in the scope and assigning a new name to it. So it's more like C++ than, for example, Python. And the difference is that Python, for example, can execute some code on import, and here it's just introducing something into the scope, okay? Now, each contract needs to, wait, I'm saying it here? Yeah. So once we have the module with the name the same as our contract and everything, we need to declare the storage struct, okay? Each contract needs to have exactly one storage struct. This doesn't limit you in any way, by the way, because, well, if you wanted to have two storage structs, you can just, combine them as two fields of one parent storage struct. It's perfectly composable in that way. But yeah, well, first you need to tell inc that this is actually the storage struct, and it just basically, well, tells the inc compiler that, okay, this piece of data needs to be actually put on the blockchain. So it needs to have a certain memory layout and everything. It's slightly different from like your regular storage outside of the chain. But you just need to remember to include this macro. And yeah, the derived default, we are going to talk about that. But for now, we are just going to say that it's a way for the Rust compiler to basically give you the default implementation of your struct. It can figure it out. Basically, whenever you want to create an empty struct, you can use the default here. It's not that important since we're pressed for time. Right, so since we're doing an ERC20 token, I think everyone knows what you need to do. It needs to have a total supply, which will be just a balance. And balance is just an alias that the inc contract macro gives us. And the balance is mapping. So, kind of things like a bank which keeps track of the balances of each individual account. It's actually the same way here. It's a mapping between the account ID, which is like the account from the native blockchain. So it's the same account that you use to interact with the chain natively. It's also here to basically keep track of balances. Well, and obviously the balance that it maps to. By the way, if you don't know structs in Rust, they are very similar to, say, structs in C++ or maybe, well, objects in JavaScript, maybe. But they are just very simple, very minimalistic. So you can, they have some fields. You can address the fields by their name, but there's no weird inheritance. So Rust actually does subtyping in an interesting way, but we don't need that for the smart contracts, just to tell you that it is there. But for structs, there's no inheritance, which I think is an amazing design choice, and I applaud the creators of Rust every day. No, I'm joking, but it's a really good choice. Yeah, okay. I think we can move on. We have the storage. Yeah, the default, we're going to skip that because there's not enough time. But essentially what this derived does is creates an implementation like that. Basically, Rust has traits, which are, well, kind of like interfaces, and you can implement them for your structs, and then you can call the operations from this given interface on your struct. Here it's default, and you can see that it just delegates the default call to the individual fields. That's how it can be done automatically, actually. So basically, the default, if you're familiar with category theory or algebra, the default value is basically the zero of a monoid, if you're into that. But it's really not necessary to know in order to write smart contracts successfully. Yeah, let's skip that. OK. Each contract, again, as enforced by the inc constructor macro, needs to have at least one constructor. And this is basically the entry point. This is what gets called when you're creating the contract as an owner, right? So we're instantiating it for the first time. So here, well, it takes some arguments, obviously, and it actually creates the instance of, well, itself here, but it's basically I could as well write Pitcoin instead of self, because it's just this, the same thing. It's just a bit more generic when you use self, but don't worry about that for now. So the cool thing about the constructors being just functions marked, or actually methods marked with the constructor macro, instead of having a predefined name like init or something, is that, well, first of all, you can choose the name for yourself, which may fit your particular use case a little bit better. You might choose initialize, you might choose, create, or I don't know, even maybe mint in some instances would be okay. Secondly, you can have as many constructors as you like, provided that it's at least one. And yeah, that's it. So here we are doing a very simple thing, actually. We are creating a variable called balances, where we are assigning a default mapping. Remember the default? It's here again. A default mapping is basically an empty mapping, right? And then we are using this magic env function called on the class itself to get the color of the smart contract, because it's quite important for the smart contract to know who's calling it. And it also can know its own account, because each smart contract is an account on the blockchain. Here we want to know who's calling us, because if someone is calling the constructor, it's the owner of the contract. So yeah. So now we know that if I'm the one creating the coin, I own the initial supply initially. So OK, this tracks. Should we finish? OK. Yeah, no, sure. Let me just finish this slide, and then I'm off. Initially, the owner will have the whole balance, right? So our mapping initially is just the owner has all of the initial supply, and we can just create this instance. And if you want to see the rest of this whole conceptual journey, yeah, let's go to alephzero.org/developers, where we have some tutorials that are pretty comprehensive. And yeah, see you on the internet, writing smart contracts. Sorry, I had like 3 times more, but miscalculated the time. OK, see you, everyone.